There is also mechanical forces involved in it that people haven't looked very much. If you look at for example, this little gypsy moth, and this is one of the best sensors that you can see. This is a cochlear hair in the ear, and when we hear the sensation of sound, basically it moves, open up the ion channels. And in chemistry or in chemical sensing, when molecules adsorb on a surface, it's also stress the surface. And that's what we are going to use to detect the molecular absorption. So what we do is that we make cantilevers, which are microfabricated from silicon. And as you can see, this is looking at the side. And we immobilize antibodies or enzymes or whatever you like to do, detect on the surface, and then expose it to the chemical or the biomolecules. When the molecules adsorb, it produces a stress, provided the absorption is happening only on one surface, not on both sides. And that you can see it here. And there are simple equations. Basically, surface stress is like surface tension, and anything that adsorbs on the surface changes the surface tension. And surface tension is a stress, so if it's happening only on one side, not on the opposite side, then there is a differential stress and the cantilever is going to bend. And you can make the cantilever as a free cantilever, like a diving board, or you can have a bridge, as shown here. So this is some of the devices that we made. There are 32 of those cantilevers sitting in a little microfluidic channel. And all of these cantilevers are around 120 micron or so. And when the cantilever bends, we also embedded a little piezo-resistive element, which is a boron-doped silicon. So the resistance changes a little bit. So you can measure the resistance, and you can get 32 different signals coming at the same time. But this is a physical sensor. It's not a chemical sensor or a biological sensor. You have to make them chemical or biological sensor by doing the things Gillian talked about. You can pattern the surface, you can add things, you can put nanoparticles or biomolecules. And then you have to have some kind of a linker, because you're talking about the stress, you're talking about the force. So it has to be attached strongly to the surface, and we have some devices by which you can deposit these materials and then functionalize the surface. And here is an example we did for US Army looking at the ricin. So they have some ricin antibody that we immobilized on the surface, and then we send the ricin in. This is done in solution. And you can see the cantilever is bending. That's on the x-axis, and as a function of time, it takes a long time, to around 30 minutes or so. All the molecules are slowly diffusing in on the surface. Bend the cantilever, it reaches an equilibrium because of all the receptors are taken. This particular experiment is done with an optical beam deflection instead of piezo-resistive element. We just reflected a little laser off and detected the bending using that method. I will talk about piezo resistance next. And here, this is a piezo resistive method. This is actually done for, again, US Air Force. They were interested in detecting H1N1 flu. So basically, we immobilize the surface, as you have seen this. And there are two cantilevers. One is a reference cantilever, and one is the functionalized cantilever. And when we send the analyte, and they bend differentially. So you're looking at a differential signal. So that means you can walk around with these things. You can hit the sample or hit the chip, and since they both will move at the same time, the differential signal cancels out all kinds of external noise. You get only the signal due to the chemical absorption. And here is the data. This is pretty new, and here is the blue arrow that is showing when we injected H1N1, actually is a peptide, and then you can see that it bends. This is another example for, you can also use it for a detection of ions. We have done it for different ions like uranium, technetium, and so on. This is a little bit more biologically relevant. It's a calcium ion. and you have to functionalize the cantilever surface, and then you send the different chemicals. Here is calcium, potassium, magnesium, sodium, and you can see that it responds very well to that of the calcium instead of magnesium and sodium and potassium. And here is another one. This is a C-reactive protein, and this again done with the piezo-resistive cantilever, and you can again see that you can see the cantilever bending when you send the C-reactive protein to the surface. And we made this device into a little small compact device, and this is looking like a little pill, and the little circular, I don't know how to use this, which one, the middle? This one is a little frit, actually, is a vapor barrier, and this is actually implanted in a rat. I will show you the data later. Basically, the vapor will go through these things, and there are cantilevers at the bottom of this thing. There are 8 of them, and all the electronics that we have designed using discrete components are there, and it works with the 2 hearing aid batteries that sit between these 2 clips. This is the open part of this thing. This is a quarter. You can see that this is actually a very tiny little device, but it can detect only vapor at this moment in time. We haven't made this in the compatible with the liquid yet. So again, these are the cantilevers. There are 4 of them, and actually there are 8. There's 2 chips sitting underneath this frit. And this is an experiment that we did with a rat. Actually, the chip I showed you before, this actually has a wireless telemetry chip here. So it can transmit the data. So you don't need any wires connected to this. So this is a standalone system. This is a little rat sitting here, and unfortunately he is not looking very happy because he's implanted with one of these big sensor. It's bigger than the rat maybe. Anyway, so what we do is that we give him some alcohol and then look at the blood gases, what happened to the metabolic product. Alcohol is one of them. We have also done cocaine and all those things for these animals, looking at the metabolic products. So again, this is another changing the shifting the focus a little bit, saying that if you look at the very small amount of analytes, whatever protein or DNA, if they are in very dilute concentration, it's very hard to detect them because we don't have enough material. So we came up with an idea using the germanium or silicon titanium oxide will work to basically using a photoelectrochemistry to collect the molecules from the solution. So this is where the solution is sitting, and his germanium is a ohmic conduct here, and this is basically forms a depletion layer. So when you shine the light, it's going to produce electron hole pairs like shown here. And you can bring either the electrons or holes to the surface. And the DNA is negatively charged, so they will come to the surface if you bring the positive charge to the surface. Or you can actually change the thing around. You can bring the negative charges and then collect the proteins which are slightly positively charged in the particular pH of the solution. So basically, wherever you shine the light, the analyte will come, and so you can actually pre-concentrate this thing. This is actually a little movie. Hopefully it will work. So this is the point. This is a piece of germanium, and we are shining the light here. This is using a LED, and you can see that all the protein is now collected here. And then we move the light up here, and then all of the move out there, and then we can keep moving it. So this is basically collected, and we moved the protein to a specific location. And we want to have a cantilever sitting somewhere here, so we can actually detect what is pre-concentrated on the surface. This is actually a movie. I don't think it will work because here we can actually separate them. We can combine them. You can move it around, and this can be done very fast. Unfortunately, this is not I cannot show you the movie.